A modern leader-class motorcycle weighs roughly 200 kilograms and produces over 200 horsepower. When that 1-to-1 power-to-weight ratio hits the asphalt, the immediate mechanical result should be the instant destruction of its own traction. Look at the BMW S1000RR. It houses a 999cc inline-4 engine, pushing nearly 210 horsepower. It is a machine engineered to operate at the absolute extreme of the performance envelope. That massive power output is bolted inside a lightweight, highly agile frame. This creates an incredibly dense concentration of kinetic potential, waiting to be unleashed. This diagram illustrates the physical bottleneck. All 210 horsepower generated by the engine must be transferred to the ground through a single surface area no larger than a credit card, the rear tire's contact patch. The ultimate limiting factor for superbike speed is no longer what the engine can produce internally. It is the external physical limit of traction right at that tiny patch of rubber. If a rider applies 100% throttle to a 210 horsepower engine with no algorithmic intervention, the immediate torque generated will drastically exceed the tire's coefficient of friction. This model shows the two immediate physical failures that follow. As the rotational force overcomes the available grip, you either get catastrophic longitudinal slip, which spins the tire out, or uncontrolled chassis pitch, which flips the bike over backwards. A human rider simply lacks the microsecond reflex speed required to manually feather a throttle and stay exactly within this tight, shifting friction boundary under extreme load. This is why historical machines like the Suzuki Hayabusa had to rely on a different approach. They used massive engine displacement, heavy overall weight, and a long, extended wheelbase to maintain physical stability. Achieving maximum velocity on a modern leader-class bike requires a system that can resolve these physical conflicts in real time. It is a task that now relies entirely on automated software intervention. We have to deconstruct the traditional idea of a throttle. On modern superbikes, the grip in the rider's right hand has no physical mechanical connection to the engine's butterfly valves. When a rider twists the grip, they are not dictating engine output. They are merely sending a digital request for acceleration. This schematic maps the process. A digital request enters the engine control unit. Instantly, the ECU pulls sensory data, pitch, yaw, and differential wheel speed. Based on these calculations, it issues spark and valve commands to limit tower. The motorcycle is operating as a high-speed computational network. It acts as a mandatory, unyielding safety layer between human ambition and mechanical reality. The first major system in this network is Dynamic Traction Control, or DTC. Its primary objective is to manage longitudinal slip during hard, straight-line acceleration. To do this, the computer continuously compares the rotational speed of the rear driven wheel against the unpowered front wheel. This visualization demonstrates the trigger point. If the rear wheel begins rotating faster than the front by a specific programmed margin, the system instantly recognizes a loss of forward grip. In milliseconds, the ECU cuts fuel or spark. It reduces engine torque just enough to allow the rear tire to bite back into its traction threshold. Dynamic traction control is an active performance tool that holds the tire at the absolute edge of its friction coefficient to maximize forward thrust. Now shift the physics problem to cornering dynamics. When the motorcycle is aggressively leaned over, it relies on the very edge of the tire profile. Dumping 210 horsepower mid-corner introduces the risk of lateral slip. The rear tire will aggressively step out sideways. If it suddenly regains grip while sliding, it triggers a violent high-side crash. This is where slide control takes over. The ECU constantly calculates the bike's yaw rate, its rotational axis relative to the actual direction of travel. Look at this cornering schematic. Instead of cutting power entirely, slide control modulates the torque. It maintains a specific, mathematically permitted drift angle, allowing the rear wheel to slide just enough to pivot the bike out of the turn. Slide control takes what would physically be a disastrous loss of lateral traction and transforms it into a controlled steering advantage. Going back to that 1-to-1 power-to-weight ratio, we have to account for violent weight transfer under acceleration. When maximum longitudinal force pushes the mass of the bike backward, it forces the front wheel to lift off the ground. That vertical pitch effectively halts your forward acceleration. To counter this, onboard inertial sensors read the exact pitch angle of the motorcycle in real time. The ECU responds by precisely limiting torque to lower the front end. It allows the wheel to hover just millimeters off the tarmac. Wheelie control is entirely misunderstood. It is not designed to prevent stunts. It is designed to actively redirect wasted vertical rotational energy back into pure horizontal velocity. The ultimate test of all these simultaneous physical limits is the dead-stop track launch. Launch control synthesizes dynamic traction control, slide control, and wheelie control into a single, automated multi-system event. The rider's role is stripped down to the basics: pin the throttle wide open and dump the clutch. The computer takes over, managing the RPM limit, rear wheel slip, and chassis pitch all at exactly the same time. This removes human inconsistency. Even professional racers cannot manually balance all of these friction limits as perfectly as the software can. Launch control provides the definitive proof. An algorithm is infinitely more capable of managing the raw physics of 210 horsepower than human reflexes. Under rigorous race conditions, a pack of Superbikes navigates complex track sectors by continuously triggering thousands of micro-adjustments per lap. Operating a Superbike is a collaborative partnership between human ambition and digital safety parameters. The human takes on macro-level management. The rider is strictly responsible for dictating the trajectory, choosing the racing lines, and submitting overall velocity requests. This diagram illustrates the micro-level execution. The ECU takes those broad rider requests and translates them into thousands of invisible physics calculations per second to keep the tires adhered to the road. The rider navigates the track layout. The onboard computer navigates the laws of physics. When you compare the top-tier Superbikes battling at the front of the pack, their mechanical hardware and peak outputs are practically identical. The advantage between winning and losing is no longer found by simply adding more engine displacement or brute mechanical force. A motorcycle's true superiority is now determined by the refinement of its algorithmic code and the sample rate of its onboard sensors. Performance is no longer a matter of mechanical brute force. It is now a product of high-frequency digital control. The limit of modern Superbike velocity is not the amount of horsepower the engine can produce. It is the processing speed of the computer translating that